Okay, so good evening. As I mentioned last class, I'll go a little over time today. I want to complete up to the sign multiplier. Okay, so I'll have to cover 3 topics. Okay, I think normally I would have covered 2. I'll just take a little bit of extra time, maybe 20 minutes extra time to go and finish the 3rd topic. Okay, and after today's class, you should be all set to finish the next assignment also, right? You should have all the information. You can go ahead, implement, do DRC, LBS, layout, everything. Okay, so that's the aim of today's class. So please pardon me, I'll go over time a little bit. Hopefully I won't have to take an extra class. Okay, somewhere. That's the aim. And before I start, our friend has lost an iPad in this class. Last time, Hemant. So if someone is playing a prank, please return it. Okay. He's desperately looking for it and we are not able to locate it. Okay. So if you find it, or if you saw someone playing a prank with it or something, then please come up and just tell him right now. Okay. Because he has a lot of information in it, and of course it's also very expensive. Okay. Okay. So with that, let's get started. So in the last class, we covered all the theory behind signed arithmetic, right? How to deal with 2's complement numbers, how to deal with sign extension of 2's complement numbers. Then we looked at some examples of how you can do multiplication of 2 signed numbers, right? And where if you don't do sign extension properly, you will not get the answer correctly. Then also the final carry out that you get from the circuit, right, from this multiplication should be used to propagate as many sign extension bits as you want. Okay, that's the use of the carry out in a signed multiplier. In an unsigned multiplier, the carry out forms the most significant bit. In a signed multiplier, the carry out is not the most significant bit. It is only to help you do sign extension to as many bits as you want. Okay, and keep the answer consistent. This is a very key difference between the 2 multipliers. So very obviously, the way you do signed multiplication and the way you do unsigned multiplication are very different, which means that if I give you an n-bit number, unless I tell you whether this is a signed representation or an unsigned representation, you cannot perform the multiplication. And that's why in your microprocessor, you have 2 different instructions called mul and imul, right? If you take the x86 architecture, there is mul and imul. One is signed multiplication, other is unsigned multiplication. Okay? And today we will see why that hardware also has to be different and how it has to be different. Okay? Okay. So let's start of an array multiplier. As the name suggests, what am I going to create? An array of full adders, basically, right? So let us take a simple example: x3, x2, x1, x0, y3, y2, y1, y0. Right? So if you look at the partial products, it will be like this: x1, y0, x2, y0, x3, y0. Then I'm going to shift and add. Okay. So what is this? It is x0, y1, x1, y1, x2, y1, x3, y1. Okay. Then again another shift. It is x0, y2, x1, y2, x2, y2 and x3, y3. Finally, you do one more shift and add, and what will you get? You will get x0, y3, x1, y3, x2, y3 and x3, y3. Okay, what is this, by the way? This is basically x into y. right? And if we are going to write y as in the binary representation, it is 2 power j into yj, right? J equal to 0 to n minus 1, right? So if I write this as if I expand it, it will basically be y naught into x plus 2x into y1 plus 4x into y2 plus 8x into y3. That's what this shifting operation is. This is basically x y naught, x times y naught. This shift and add is basically 2x times y1. This is 4x times y2 and 8x times y3. Okay, this is the shifting and adding part that we are doing here. So now my task is to basically place full adders so that I can accomplish this task. Okay, yeah, so that's okay, I can keep the multiplier there. So now you should tell me what these blocks are, okay, whether these are half adders or full adders, and how do I cascade them, how do I connect them. So this is Z0, Z1, Z2, Z3, Z4, Z5, Z6, and I have a Z7 also. So you have to tell me where these Z0 to Z7 variables are going to come out of this circuit and what these individual blocks are. Okay, clearly these are AND gates and they are creating my partial products. X0, for example, this is what? X0, Y0. Yeah? And this is X1, Y0, X2, Y0, X3, Y0, and so on. Right? So first of all, where is Z0? This is Z0. Okay. Now I need to perform which one? This addition. X1 Y0 plus X0 Y1. So what block should that be? Half adder. Basically because there is no carry, right? Half adder. What about the other adders on that same row? They are all. So for example, you have to perform X2 Y0, right? And X1 Y1, right? This block. If you look at it, this is what we are performing here. So that will also be a half adder, right? So everything here will be a half adder. Okay. So you add these two numbers, X1 Y0, X0 Y1, you get a carry, right? That carry is now going to propagate from this red to this blue block. Correct? Because I need to add it to my next set of terms. Correct? So what will be the carry out direction? Okay, assume that my half adder block is like this. Okay, it takes A, B, C in, gives C out and sum. Sorry, full adder. Okay, half adder is you just ground that way. That's all, there's no C in. So what is the direction of flow for the carry out on the first row? Right, so what we are doing is we are taking this carry, propagating, then we add those three numbers, we will propagate like this. Correct? Or not even those three numbers, I am adding those two numbers and then propagating. Correct? So first of all, can that be a full half adder at all? In the way I am showing you here. Why? Because I'm propagating the carry. Therefore, this has to be these blocks have to be full adders. Right? And I'm going to propagate my carry like this. Okay? Now, what is the output of this half adder in red? That is nothing but Z1, right? So, this is going to be my Z1. Which one? The final one can be because there is no other term coming in. That is also true. Very good. Okay. So, this can be a half adder. Correct, no? He's right because there is no other term coming there. Okay. So, now what about row 2? So, the first full adder in blue, right, this guy, what did we do? We basically added x2 y0 with x1 y1 and propagated the carry. What about that sum? That should get added to x0 y2, correct? So, therefore, the sum has to propagate like this. Correct? Now, what is there a third input to this block? Yeah. That's a good point. True. No, it's not actually more adders. I'll come to that. No, the aim is not to reduce the number of adders. The aim is to do it as fast as possible. So, we'll come to that. It turns out that by doing what you said, you'll actually speed it up by putting in more adders. I'll come to that. That is the next architecture. Why not? Because I get x1 y0, x0 y1, I get a carry, right? I'm going to add that carry here, right? So, basically I'm adding these three numbers. No, again the carry, right? From each addition that I get a carry out. I have to take it to the next stage. No, the carry always goes to the higher bit. It goes to the 2 power 1 into something plus the sum. The carry does not affect the sum. That goes to the next bit. Correct. Correct. That will not affect the value of Z2 is what I am saying. Because the carry is going to the higher bit. See, this is 2 power 0 into Z0 is the coefficient of 2 power 0. Z2 is the coefficient of 2 power 2. Right? That carry that comes out of the addition of x2 y0, x1 y1 and the carry is actually going to 2 power 3. So, therefore, it will not affect this Z2 which is the coefficient of 2 power 2. Okay, so maybe, see the carry might be 0, which is fine. But if the carry is 1, then it has to go to the next one, right? Functionally, this is fine. it turns out it's a different thing that timing wise it may not be very efficient. Okay. So let's proceed. We'll come back to your doubt if it still exists after some time. Okay. So now the second block, right? Again here the sum has to basically come down. Correct? What about the second block? What should that be? The first one. Half adder again, right? This is a half adder. This one, full adder, half adder. Right? We have to be careful here. Okay, for now we'll keep it as half adder. The last stage again, half adder, full adder, full adder and half adder by the same logic. Correct? So now what happens to the carry propagation again here? It's going to go like this. Right? And of course the sum has just come down like that. Okay. So what is this term here? Z2. This is Z3, Z4, Z5, Z6. Right? Now what happened to the carry out from those left corner half adders? I am adding x3, y1 here. X3, y1 with the carry from the x3, y0, x2, y1 term. There is a carry out coming. I add those two terms. Where does that carry go? So that has to come here. So now can this be a full half adder? So it has to become a full adder. What is the term we are missing now? Z7. Z7. That's coming out from the last full adder there. Right? So this basically tells you how to line up array of full adders, right? Even the half adder I can consider the full adder, right? When you're trying to make an array structure, you don't optimize on that area there. You take a full adder and repeat it. I'm just calling it half adder, full adder so that it makes it more clear. Okay, otherwise they're basically just full adders. So in order to perform 4 cross 4 multiplication, how many half adders or full adders do I need? Yeah, n into n minus 1, right? So therefore you need n into n minus 1 full adders effectively, right?